When you're streaming on Netflix or just doing a quick Google search, you're tapping into this giant network of thousands, even millions of computers. So what happens when one of those computers just, poof, disappears? How does a system that big even notice a silent failure? Well, that's the supercritical puzzle we're going to try and solve today.
I mean, think about it for a second. A failure isn't always some big, loud, obvious crash, right? A server, which is really just a computer, we call it a node in the network, it can just become unresponsive. It stops sending messages, it stops doing its job, and it goes completely quiet. And for a system that absolutely relies on teamwork, that silence, that is a huge problem.
It's kind of like being on a project team at work. Imagine one of your colleagues just suddenly goes silent. No emails, no Slack messages, nothing. How long would it take for you to notice and, reassign their work so the project doesn't grind to a halt? Well, computers face the exact same challenge, but their reaction time has to be in milliseconds, not hours, not days, milliseconds.
All right, so let's actually put a name to this whole challenge. In the engineering world, this is what's known as the silent failure problem. And let me tell you, it is one of the toughest nuts to crack when you're trying to build these massive, super reliable systems.
The key word here really is active. The system can't just sit around and wait for a failing server to send a nice little farewell message saying, "Hey, I'm about to go down," because that pretty much never happens. No, the network itself needs a way to actively and constantly check in on all its members. It's like a continuous roll call, 24/7.
So the big question is, how in the world do you actively check on thousands or even tens of thousands of servers at once? Well, let's take a look at the most obvious ideas first, and then we'll see exactly why they fall apart when you try to scale them up.
Okay, so two pretty simple ideas probably come to mind right away. But, spoiler alert, they both have some major flaws. On the one hand, you could have a single boss server. Its whole job is just sending out little pings to check on everybody else. But what's the problem there? Well, if that boss server fails, the entire system goes completely blind. That's what we call a classic single point of failure. Not good. Okay, so on the other hand, you could have every server ping every other server. That gets rid of the boss problem for sure, but can you imagine the chaos? With thousands of servers, it creates this insane network storm. It's just totally unscalable.
So, if a centralized boss approach is way too risky, and the all-to-all method is just way too noisy, what's left? What's the smarter, more elegant solution? Well, it's a protocol that's actually inspired by something we're all, let's be honest, pretty familiar with: gossip.
And at the core of this whole gossip idea is something called a heartbeat. It's exactly what it sounds like. Just like your own pulse, it's this regular, rhythmic signal. Each server is constantly sending out a tiny little message that just says, "Hey, I'm alive, I'm still here." And if another server stops hearing that pulse, well, that's the very first sign that something might be wrong.
Okay, so this whole gossip protocol really boils down to two key pieces. First, every single server keeps a little list. We call it a node membership list. You can think of it like a phone book, basically, a directory of all the other servers and what their last known status was. And second, each server has its own heartbeat counter that's just always ticking up, 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 up. It's a constant, undeniable proof of life.
So how does this all actually work in practice? It's kind of like a simple four-step dance. Step 1, every server is constantly ticking up its own heartbeat counter. Tick, tick, tick. Step 2, every so often, it doesn't shout its status to the whole world. Nope, it just gossips. It sends its whole list to a few random neighbors. That's it. Step 3, now, when a server gets one of these lists, it merges it with its own. But here's the clever part. It always keeps the highest, most recent heartbeat count for every single server. And that brings us to the final step, number 4. If a server looks at its list and notices that another server's counter just hasn't updated in a while, it starts to suspect that server has failed. So simple, right? But it's incredibly effective.
Okay, I know that might sound a little abstract, so you know what? Let's just walk through a quick step-by-step example to make this crystal clear. Let's see it in action.
All right, picture this. We're starting with a perfectly healthy network. All our servers, our nodes are online. Their little heartbeat counters are ticking away, just as they should. And every few seconds, they're gossiping their status updates to each other. Everything is humming along smoothly.
And then it happens. Out of nowhere, Node S2 just silently crashes. It stops doing any work, and this is the crucial part, its heartbeat counter freezes. It's stuck. Now the other nodes in the network, they have no idea this has happened. Not yet anyway.
Now watch this. Server S0 is just about to do its regular gossip, but as it looks at its list, it notices something's off.
The heartbeat counter it has for S2, it looks stale. It hasn't changed in a while. So what does S0 do? It marks S2 as suspected in its own little directory, and then it gossips that newly updated list to a random neighbor, let's say node S4.
And this is where the real magic of the protocol kicks in. That little piece of gossip, hey, S2 is suspected, it starts to spread like wildfire. S0 tells S4, then maybe S4 gossips with S1, S0 gossips with S3, and before you know it, through these random exchanges, the entire active network comes to the same conclusion. S2 is offline. And the best part? There was no central boss making the decision. It was a consensus.
Okay, so that's the how, that's the mechanics of it. But let's ask the really important question. Why? Why is this process so incredibly critical? Why do we go to all this trouble just to figure out if one server has gone offline?
This quote right here really nails it. You see, a simple temporary network glitch could easily make one server think another server is down, even when it's perfectly fine. You just can't take one server's word for it. And that's why the gossip protocol is so powerful, because it's not about one server's opinion. It's about helping the entire system build a reliable consensus before anyone takes drastic action.
And this is why it all matters so much. Once the system agrees that a server has failed, it can finally act. This is what enables things like high availability, because now traffic can be instantly rerouted away from the dead server. It ensures reliability, because the system can automatically trigger recovery actions like promoting a backup database. And at the end of the day, it creates resilience. It's what allows the system to take a hit, to absorb a partial failure without the whole thing collapsing.
And really, that's the key takeaway here. Detecting the failure? That's just the beginning. That's step one. The real magic of these massive systems is the automated recovery that happens next. Which leaves us with a final, pretty cool question to think about. Once a failure is confirmed, what happens next? How does a system automatically heal itself? Now that is the very essence of resilient design.